In a depth versus time situation, if we have 3 xy points and we expect or anticipate a quadratic model, we would substitute the coordinates of the 3 points into the form of the quadratic function, y equals ax squared plus bx plus c, and obtain 3 equations represented schematically here. I haven't written numbers in here because I don't have specific x's. Again, this is a review. This is just to show you where we go with this. You should recognize this immediately and understand how we solve these equations. And if not, of course, you need to review some. Consult the class notes as published or on CD. We get a solution here anyhow. The solution we get is numbers for A, B, and C, the 3 unknowns, which we then plug back into the model. A, B, and C will now become numbers, and we'll have the numerical model. If we want a depth versus clock time interpretation, and we want to get a depth from the clock time, then we substitute the clock time in for x. Might have been better to use t for the variable here, but we can use x and just understand that it's t, that x stands for clock time, and we're going to substitute t values in for x. In any case, we get a model y equals ax squared plus bx plus c. We substitute t in here, and we can immediately get y. So given the clock time t, we get the depth y. Now, if we want to find the clock time at which a given depth occurs, then we're going to substitute that given depth, which we'll call y, in for the y here. So this will become a number. And at that point, we have a quadratic equation. We can solve this quadratic equation for x, which stands for the clock time, and our solution, x, will be our clock time. So we'll say t equals x, where x is our solution. If we want to do a linear model, and I think the model mentioned in the problem was a model of flow range, the distance the flow goes before hitting the floor or the pavement or the ground or whatever, then we'll use a y equals mx plus b model. And if we have 2 representative points, not necessarily data points, but 2 points that represent what we actually think is going on, we can substitute the coordinates of those points into the y equals mx plus b and get mx plus b equals y. Y values go here, x values go here. We've got 2 points, so we get 2 solutions. Solving the system, we get m and b, which we substitute into the form of the linear equation, and we get a linear model. This model can be solved for y or for x. So if we're given a value of x, we want to solve for y. If we're given a value of y, we want to solve for x. A model that we used, and a model that's again mentioned here, is spring length versus weight. If y is the spring length and x is the weight on the spring, then instead of using y and x and trying to remember which one is spring length and which one is weight, why don't we just write out spring length equals mass times weight plus b, and treat spring length as a variable and weight as a variable. If we put in weight here, we multiply it by whatever m is and add whatever b is, and we get the spring length. Conversely, we could solve this equation for the weight to get a formula that allows us to put in the spring length and determine the weight. To solve for the weight, we'll subtract b from both sides, then divide by m. So we'll have spring length minus b over m. So if we put, actually, I've got this backwards, we get the weight from the spring length. If we put in the spring length, we get a weight.